To understand linear programming better and deeper, let's learn about some terminology and concepts in linear programming. So we learn about the extreme points or coordinate points. First of all, after you, in the graphical method, after you implemented and plotted the constraints, the common feasible area is called the feasible space or feasible solution space. And then there's going to be corner points which are located at the intersection of different constraints. Those are called corner points or extreme points. Within those areas are called the interior points, any points. There are infinite number of interior points within the feasible space. So we learned, I told you about a theorem which states that the optimal solution of a linear programming would occur at the extreme point or corner points. And since we're going to have a limited number or finite number of extreme points, countable number of extreme points, one way actually to solve linear programming is after you, for example, in a two-dimensional space, for when you have two variables, you can actually numerate and count the extreme points and plug in the coordination of those extreme points and corner points into the objective function and find the objective value for those extreme points. And according to the problem statement, whatever, if you are minimizing or maximizing, find the minimum and the maximum of those values, and that's going to give you the optimal solution. This is called the enumeration approach. At the optimality state, that means that suppose that we have found the optimal solution. And we learned that the optimal solution in linear programming is going to be an extreme point or a corner point. So here we want to study the state of the constraints in the optimality state. In the optimality states, we have for the constraints we have two states: binding constraints and non-binding constraints. Binding constraints are those constraints that they would actually constitute or build or create the corner point and the extreme point in which the optimal solution occur. Let's see this example that we previously went through. So our optimal solution here is this point. This is our optimal solution. And if you look closer, you're going to see that this extreme point is built by two constraints. The inspection constraint and the storage constraint. So these two constraints, the inspection constraints and the storage constraints, these are called binding constraints. On the other hand, the assembly constraint here, this constraint does not form the extreme point of the optimal solution. So the assembly constraint here is a non-binding constraint. All right. So let's now go to the mathematics of the binding and non-binding constraints. I'm going to write a general formula for the constraint. Suppose we have a multiplied by x less than equal to b. So we have the left hand side of the constraint and we have the right hand side, which is a value, a parameter. It's just a number. And then we have the inequality sign here. Okay. So at the optimal state, if we have a binding constraint like the storage constraint here or the inspection constraint here, if you substitute the optimal solution, I'm going to show it by x star. X star is the optimal solution. If you substitute it into the decision variable, then what's going to happen is these both sides would be actually equal to each other. So at optimality state, at optimal solution, the left-hand side of the constraint, the binding constraint, is equal to the right-hand side of the binding constraint. This is not true for the non-binding constraint. For the non-binding constraint, if you have less than inequality, and if you substitute the optimal solution, the left-hand side would be strictly less than the right-hand side. Okay. So this is actually very important. This is also true for the greater than equality. So if we had ax greater than b equal to b, and if this constraint was a binding constraint, if we substitute the optimal solution, then again these two sides would be equal to each other, okay, for the binding constraint. Okay, so why this is important? The binding constraint are those that all the resources for that constraint have been actually used. So that's why the left-hand side, which is the consumption of the resources, is equal to the right-hand side, which is whatever you have from that resources. Okay. So for example, here the storage, the amount of storage that the company has, all of it has been used by the optimal solution value or the decision variable, optimal decision variable, and also the inspection time as well. So in this setting, if this company invests on improving, for example, the assembly time, it would not improve the objective value, the optimal objective value. So if they want to improve and increase the whatever the objective is, for example, profit here, maximizing profit, then they have to invest on the resources that are associated with the binding constraint. So what that means is they have to invest on storage and invest on the inspection. They have to increase inspection time and storage resources so that they can improve the optimal solution or the profit that they make. For the non-binding constraint, it doesn't matter. For example, the assembly. For the non-binding constraints at the optimality state, we have two concepts called the surplus and the slack, depending on the constraint inequality sign. So if we have a greater than or equal to constraint, for example, ax greater than or equal to b, at the optimality state, if we actually substitute the optimal value of decision variable, for the non-binding constraint and greater than or equal to, we're going to have a strict inequality here. This means that the right-hand side of the inequality is greater than the right-hand side. The left-hand side is greater than the right-hand side. So this means that we have a surplus here. We have a surplus. So when the value of decision variables are substituted into a greater than or equal to constraint, the amount by which the resulting value exceeds the right-hand side, it's called a surplus here. So the surplus here would be ax star minus b. This would be the amount of surplus that we have. If we have a less than or equal to constraint, for example, ax less than or equal to b, at the optimality state, if we substitute the decision variable by the value of the optimal decision variable, for the non-binding constraint, this is going to be a strict inequality. And the amount by which the left-hand side is less than the right-hand side, that means b minus ax star, this is called the slack. So at the optimality state, we either have binding constraints or we have slacks or surpluses. Another type of constraint are redundant constraint. A redundant constraint is a constraint that does not form the feasible space, does not restrict the feasible space. So for example, let's see this in this graph as you see here. This is the optimal, this is the feasible solution space, which is bounded by these three constraints. The inequality constraint here, the inequality constraint here for x2, and this constraint here. These three constraints build the feasible space. On the other hand, these two constraints, this constraint and this constraint, these two do not have any role, do not restrict, okay, do not form the feasible space, right? Do not bound. So that the feasible space is only bounded by the three constraints here. Okay, so these two constraints then, the blue one and the green one here, they are called redundant constraints because if you get rid of them, if you do not impose those constraints, the feasible space would not would be intact, would not change. So they are not important in our model or in our problem. These are called the redundant constraints. That means that you can just get rid of them. You can just not you can ignore them and not include them in the model. You can just delete them from the model. We learned about the state of constraints at optimality state. Now we want to look at the state of variables at optimality state. Suppose that we have solved a linear programming model and we have found the optimal decision variables. And I'm going to show it by X bar. So X here is capital X, and that stands for an array of decision variables. So that means that there are more dimension here. So suppose that we have n dimensions. So x1, x2, x3, and xn. Some of these variables, their value is 0, might be 0. So those that their value is 0, suppose that x3 star is 0, these are called non-basic variables. For those that their values is not 0, that means it's greater than 0, it's a positive value, they are called basic variables. So how is this relatable? So for example, if x1, x2, x3, each of these are the decision variable to make product 1, type 2, type 3, the basic variable means that produce these types of product, and the non-basic variable says that, okay, do not produce these types of product. For example, produce zappers or produce space rays or whatever the context of the problem is.